Today we'll start with the electromagnetism, and actually this chapter is very briefly explains the electromagnetism concepts. So if you go to physics department, the 200 level, there's an introduction to electrodynamics, and this chapter summarizes this book. Okay? And we are learning for 2 classes. So just keep in mind that we are doing really briefly. So if you want to review more, then please refer to this book, The Introduction to Electrodynamics, written by Griffiths. Today we'll talk about the charges and static charges and moving charges and time-varying field and the material medium. So up to 10.5. So what is charge? Electric charge. See, basic element of charge is the proton and electron, right? So, and we have, yes, okay. The magnitude of that charge is the 1.6 times 10 to the negative 19 coulomb. The unit C is the coulomb. And if there's a cloud of the charge, so this is the charge cloud, then we can define this charge cloud with the charge density. It could be volumetric density, or if there's an area, for example, like we have a clay particle, and if there's a negative charge, we have always the negative charge in the clay particle, and then this charge density can be also defined as total Q over A, or here the total Q over volume, right? So surface charge and this rho V and the rho S are the volumetric charge density and the surface charge density. And charge conservation. So net charge in the universe or in an isolated system is constant because electric charges cannot be created or destroyed. So the electron or the proton cannot be created or destroyed. So the charge conservation can be applied. Yep. So if a body or volume is enclosed within a surface, the total current across the surface must be equal to the change in the free charge enclosed. So I think this is the same with the conservation or the continuity equation. So for example, if there's an area surface like this, then inside this charge, the charge enclosed, and if there's a current, and then so the change in this surface, it's change in the total charge in the surface is the same with the current density, integral of the current density. This is a surface integral. And using the divergence theorem, we can convert this surface integral into volume here. So divergence of current density. So here, divergence of current density and dV volume. And then we can cancel the integral, the volumetric integral, and then this only remains. Right?
That's why the minus sign on the right side is not in the divergence.
Here. Good question. 왜일까? Why? Anyone? I think it's according to the definition. That's a good question. I have no idea right now. I'll find out and I'll let you know. 빠진 것 같다고? Okay. Okay, let me check again. Could be because of the by the definition, or it could be mistake. And the electricity and electromagnetism associated with the static and moving charges can be expressed with the electrical field intensity and the magnetic induction. We're gonna find out soon more about this one. And math concept is just to recall some of the math concepts that we're gonna use. Divergence theorem. This changes the surface integral into volumetry integral. And Stokes theorem is a loop integral into curl of something, the volumetry integral of the curl of something. And the del operator shows the gradient of each normal vector. Right? So this is the gradient. And the terminology is, it's a little bit shifted. So let me just erase all the boxes. Conduction, polarization, and magnetization. These three concepts are very useful concept and basic concept for the geophysical survey. So DC electrical resistivity survey used the conduction, and the IP induced polarization method used the polarization, and the magnetic survey used the magnetic permeability of the material. So conduction is what? That's when you have a free charge, and if free charge moves, you have a current, right? And this movement of the free charge is called the electrical conductivity. So electrical conductivity is also the reciprocal of the electrical resistivity. Here, electrical resistivity is rho. Resistivity. So it's like you have a conductor and you have a free charge, like free electron, and when you apply the voltage, this free electron moves, right? And the mobility of that is called electrical conductivity. And polarization can be expressed as the parameter called the permittivity. So this permittivity shows the polarizability of the material. And when you have insulator or the dielectric material, so it doesn't conduct the electrical current, then for example the water or just the gas maybe, then when you have a gas, for example hydrogen atom, when you apply the electric field plus and minus, so the electric fields to this direction, then the proton or the proton is attracted to this part, and the electron cloud is attracted to this positive side, right? But they don't move, so they just locally moves a little bit. Or if you have a water molecule, they can rotate too, right? So this is called the polarizability, and so this becomes dipole moment. So that becomes a dipole like this. and how much is polarized is expressed as the polarizability. Oh, no, sorry, the dipole moment and the polarizability. So, and when you have the water, so groundwater can be polarized, right? And this is expressed as minus and plus dipole. So the ability of the medium to become polarized in response to an electric field. So you can rotate and it may have a little bit of the local mobility, but it doesn't move. The molecule itself doesn't move. And magnetization is expressed as the parameter called the magnetic permeability, and this is defined as the ability of the medium to become magnetized in response to a magnetic field. So you have a maybe iron, and if there's a magnetic field, as iron becomes magnet, right? And that ability is called a magnetic permeability. So we can define the 6 fields. For the free charge in the conductor, we have an electric displacement D and magnetic field intensity H. So this is called this area is for the electric field, and this is from the magnetism. And for the bound charge, we can define the polarization, and the magnetization. And this, when we combine the free charge and the bound charge, and this is expressed as the electrical field intensity, and the magnetic induction too. So you have, for example, in the free auxiliary field, you have electric field in the free field. So there is maybe a free charge. And if you have a medium that's dielectric, plus, and minus, oh, sorry, it's going to be the other way. So minus, so it may be clay particle, and plus, and this dielectric particle is it gives the medium effect or material effect. And inside this field, the whole electric field is combined by this free charge effect and the bound material effect. So DPE and HMB represents each fields. So we're going to talk about the static charges. So the charge, in this case, charge doesn't move. And we're going to talk about the charge moving at constant velocity. And the last case is when the field is moving or the charge moves in the different acceleration. Electric force can be expressed with the Coulomb's law, and when you have, which one is the test charge? Say this is the test charge, and this Q2 is the source charge, and we are wondering about the force that this test charge is feeling. Right? So how much force is feeling that's regulated by this Q2 source charge. Then the force is Q1, so the charge times the electric field that's caused by this source charge, or the Q1 times Q2 over R square, right, times this coefficient 1 over 4 pi e epsilon 0, and n is the normal vector, that indicates the direction of the force, or the unit vector. So this is similar to the gravitational force, right? When we talk about the gravitational force, G, or just G, M1, M2, R square. Right? And here in the Coulomb's law, we use the epsilon 0. That's the permittivity of the free space, or the vacuum, you can think of that. And if you have multiple charges, like this is Q3, Q4, and Q5, to Qi, and this affects the, results some force to this test charge. And if we want to find out the force, that's the total force exerted by all these charges, then we can just sum up each forces, right? So we can call that superposition principle can be applied. The sum of the forces generated by all other charges is F1 plus F2 plus 2 Fi, and each one will be expressed according to this equation. And then you may have a cloud of charges in some volume, right? In a volume. So then, if this is the Q in a certain volume, then this is the Q over R square, right? Equivalent to. And here the dq can be expressed with the charge density. So here rho v is Q over volume. And then this rho v, if the rho v is the constant with respect to the distance from the test charge, then we can take out the rho v, and this remains only. So you can just remember that the superposition rule is valid in this electrical force in the static charges. Yeah? Then electric field, we can also define the electric field, and this is defined as the force exerted on the positive test charge when its charge goes to 0. So here, do you see it well? If the Q goes to 0. Right? And for the point charge, so the electric field is defined as this equation. So if there is a Q and this generates the electric field in the radius direction, right? E. And if we put some charge here to find the force, then the force acting on this charge Q, Q is Q times the electric field, right? By the definition. So, what's the unit of the electric field in the case? Force divided by the charge. So, what would that be? Force is in the SI unit Newton, right? Newton divided by Coulomb. Thank you. Okay, let's consider a body with a charge Q inside. that's surrounded by a convex surface. If the enclosed body is electrically neutral, then the enclosed charge Q is 0. So if you have a surface surrounding a certain volume, then when you have a plus charge S minus charge neutrally balanced, then the net charge of this volume is 0. And let's think about this. As inside you have a cube surrounded by a convex surface, and you have a test charge that's a plus 1. And if you move this test charge and measure the electrostatic field at every point in this surface, then integral of the electrostatic field emanating across surface is equal to the enclosed charge Q. So this is from here. And if the volume enclosed consists of specially distributed charges with the volume charge density rho v, so then this Q is function of rho v and the volume. Then we can express it in terms of the integral expression with this equation. So this Gaussian, and this is called the Gaussian law of the electrostatic charges, and this means the electric field is only affected by when you have charges like this, and if you draw any Gaussian surface around it, the electric field on this surface is only affected by these inside charges. If you have another charges here, this charge doesn't affect the electric field at this surface. That's the essential of the Gaussian law. Because this electric field will just transmit and it's going to go out across the surface. So only the inside charge affects the electric field at across the surface. So then, just an example, derive the external electric field outside the ball of the radius r in which charges are evenly distributed. So inside you have charges evenly distributed, and then find out the electric field at the distance r, small r. So from the Gaussian law, so this is from the Gaussian law, electric field across the surface, the surface integral of the electric field is the same with the Q inside. This is the internal Q. And simply here the internal Q is the same with the total, the small q, and here the electric field is symmetric because if we just draw the sphere or ball, and the Gaussian surface can be also drawn as a sphere with the radius of the small r, then the direction of the E is the same with the ds. This one. So for example, if this is the unit vector ds, then this is the same with the electric fields parallel to the electric field direction. So then we can take out this one, and we can take out the dot product, inner dot product, right? So this inner dot product will go away, and this electric field will remain only their magnitude. And we can take out this one, and if we do the surface integral of this sphere with the radius of the small r, what would that be? What's the area of this ball? That's 4 pi r square, right? So if you put it into that equation, that electric field is 1 over 4 pi epsilon 0 times q over r square times the unit vector n. So this is exactly the same equation that we defined for the electric field. And this means that inside this ball, if the Q is concentrated at some point, still the electric field at here is the same. Right? This electric field doesn't care about as long as the distance that you're interested in is the outside is this Gaussian field, then Gaussian surface, then whether this charge cloud is concentrated here or concentrated here doesn't matter. Right? You always have the same electric field. So electric field does not change when Q is concentrated anywhere in the ball. It's fun, right? The general physics 2? I think you have heard the same things from the freshman year when you took the general physics 2. Okay, I'll just take out all the units, the boxes. We can define the electrostatic potential right now. So electric potential is the work required to bring a positive unit charge from infinity to a point A into the vicinity of the charged body. So when you have a Q here, test charge actually the positive test charge was at a distance of infinite, and you take it to some place here, that's the distance of A. So the potential is defined as the work, and the work required to bring that charge to a certain point is the electrostatic potential. Okay, good. So the electrostatic potential around the point charge can be defined as the 1 over 4 pi epsilon 0 times q over r. Right? And this is, we know that the Newton and Coulomb was the electric field unit, right? Unit of the electric field. And so the potential, electrostatic potential unit will be N and length over Coulomb. And this is same with the Joule over Coulomb, and this is same with the voltage, as I said here. And when you do a curve, I think that this is the same with the curve. If the charge moves in a loop, then the total work is the 0, so that this becomes the 0. Again, the potential can be defined as the line integral of the electric field. The electric field at a point can be written in terms of the gradient of the potential. So that here that you have a gradient using the del operator, gradient of the potential. And where is it? E. I think that before was it? Something like this, right? And from this relations, you have this Poisson's equation. And this tells you that second derivative of the potential is the same with the charge density over epsilon. And if the charge density inside is the 0, then this becomes 0, right? When Q is 0. So this becomes a Laplace equation then. Now, then let's talk about the moving charges in free space, and this becomes more complicated now that we are introducing the electromagnetic force, the magnetic force in here. Let's overlap a little bit. A string of charges moving in a free space at a constant velocity v. So charges moving at constant velocity v here, and then at point at a distance r, you have a magnetic force, magnetic induction B, and that can be calculated using this equation, U naught over 4 pi times Q, V times V cross product, and the unit vector over R square. And so the V here is the velocity vector, N is the unit vector indicating the direction, Q is the charge. So if you compare with the electric field equation, what is added? The added component is the V, the vector, the velocity vector, right? So they just apply the velocity vector here. And here the mu naught is the magnetic permeability of free space, and mu naught is 4 pi times 10 to the negative 7 pound per meter. So here the cross product indicates that the direction of the force B is perpendicular to both direction of movement V and the unit length vector N. So that's gonna be this direction, right? So that goes in. Is it going in or going out? Huh? 아닐걸? 여기서? 여기 charge Q가 움직이는데? I think this is not the this Q, the Q is moving at constant velocity in a line. So you can think of the electric cable. I think this is correct. Then the force can be also calculated from this B and the Q times V. So here the Q is that when you have a conductor in which the Q is moving, and here you put the Q outside this conductor, and the force exerted by this movement of this moving Q is F. And this F is Q times V and cross product of this magnetic induction field. So electrostatic field around the point charge Q is this one, and this is the electromagnetic induction, the magnetic induction field around the point charge. This is the B. And do you remember the Gaussian law? So when you have charges, and if you draw the Gaussian surface, then the surface integral of the electric field across this Gaussian surface is the same with the electric charge inside, right? But in the magnetism, you cannot have only just one, what do you call that, one pole, right? You cannot just have the N pole separated from the S pole. You will always have the N and S together, right? So the net magnetic, what would you call that, electric charge, is compensate each other by this N and S, so that the surface integral of this magnetic induction field will be always 0 when you draw a Gaussian surface. So difference here is you have a Q and you have the 0 value. So for a wire, conductive wire carrying a current I, the magnetic field around the conductor is expressed with this equation. And when you differentiate for a differential element of the wire dl, the F is the dl times the B, right? And times the current. And for an Amperian loop around the conductor, so you have a wire like this, and here the charge is moving at constant velocity. And if you draw the loop or circle, then the integral of the B across the loop is the current, and it's called the Ampere law, Ampere's law. So this Ampere's law correlates the current to the magnetic field, or the magnetic field to the current, electric current. instead of the conductor, consider a body with a current density, then you can substitute the current, electric current with the current density J. Oh, here is it. And we can have the three possibility. So you may have a static charge, that charge doesn't move, and you may have a moving charge that's moving at constant velocity v, and also the last case is that you have a magnetic field moving. Right? So in that case, so you can think of this magnet is moving back and forth, then you have a current induced inside this coil, and in the Maxwell equation that reflects the last case. And electric field, let's read it through from the first sentence. The only an electric field E can exert a force on a static charge. So this is from the electrostatic force. And the change in magnetic flux creates an electric field. That's Faraday's law. And change in electric flux is associated with the magnetic induction field. That's Maxwell's law. And when we combine with the Ampere's and Maxwell law, we have this relation. So here you have a current that's causing magnetic field, and you have the change in electric flux that's causing the magnetic field. This is actually delta electric field. So the last equation tells that the current, the moving charge causes the electric force, the magnetic force, and also the change in electric field causes a magnetic force. Good? Question? No? Okay, that's very quick. So far, we have seen the electric field and the magnetic induction field in the free space. And if we put some material inside that electric field or the magnetic field, for example, the clay or the quartz or the water, then you have an effect of the material. That's dielectric. So in that case, if you put some, like this figure, if you put some maybe clay particle inside the electric field, that the clay particle will be polarized. Then this polarized charge, so that you have a minus charge concentrated at one edge and plus charge, right, polarized at the other edge, and this P polarized material compensate the electric field. So the force resulted by the electric field, external, will be the same with the force by this polarized one. This is very natural because if the force is not balanced, then this material will move. Right? So as long as the material doesn't move, then also the inside charge doesn't move, then it means that all the forces are balanced. So that this polarization vector is added in this case when you put the dielectric material. And this will be the same with the magnetic field. When you have a magnetic field and you put some maybe like magnet or the iron that's a paramagnetic material, then this will be magnetized and that will compensate the external magnetic field. So you have another component, the P, and the magnetization vector M, and a dielectric material is placed within an electric field, the positive and negative bound charges move locally. Therefore, a net charge appears on the surface on the dielectric. One side has a positive charge and the other side has a negative net charge. And this dielectric has become polarized, we call it. Then, how can we define the polarization? And this effect of the polarization can be modeled by replacing the polarized dielectric with the surface and volume charge distribution. And so you have a bound charge density over the surface. And if you combine the free and bound charge together, the electric field is caused by this free charge and the bound charge. Then, if you separate these two, free and bound, this is the same with the minus surf P ds, right? Then we can move it to left side and this becomes the next equation here. So the electrical displacement that's caused by the free charge is function of the external field, external electrical field, and the polarization. And polarization of the bound charge P is linearly dependent on the intensity of the applied electric field. The vector E and P are parallel, so the when you have a material that's polarized, P, and this is, this could be, sorry, this will be the other way, because the electric field is this direction. If the E increases, then the magnitude of the polarization will increase too. So if you put more charges here, and this becomes more bigger, and the polarization vector also increase too to compensate that. Right? So we can see the linear relationship between the P and the E, and we introduced another concept, the electric susceptibility here. And then, so if you plug it in here, according to the definition of the electric displacement D, the electric displacement becomes the epsilon times 1 plus psi E times E. And this is the material property. And that's denoted by the epsilon. So, in the free space or the vacuum, you don't have any material inside, then this psi becomes 0. So the E becomes the same with the E naught, right? And for example, the water, epsilon is around 80. So that means that the water can be polarized. Oh, sorry. Times E naught. 80 times more than the free space. And you can apply the same concept to the magnetization. When a material body is placed within a magnetic induction field B, the body becomes magnetized. So this M is equivalent to P, and the currents appear on its surface J. And with a similar approach, we can define the magnetic field intensity H. So the H is a function of the induction field and the magnetization M. Then here the M is also linearly proportional to the H. And here the psi M is the magnetic susceptibility. Here the magnetic induction field is the mu times H plus M, and this becomes mu times H plus psi M H. And so the mu is the magnetic permeability of the material. So, paramagnetic and what is it? Ferromagnetic and diamagnetic, is it? 현우야, 맞니? 그러면 then what's the psi value for water? Because the water cannot be magnetized. It's almost the magnetization is 0. So it's gonna be same with the free space. So the psi is close to 0. Right? And for iron, I think the psi is much larger than 1. I think it's around, how much is it? 700, hundreds, right? Several hundreds of it, or the thousands of it. So we'll find out more the realistic value in the next chapter. So the bigger psi means that the material can be more magnetized for the same amount of the magnetic field. Conduction. The last one is the conduction. Conduction is how freely the charge can move inside the conductor, right? So Ohm's law defines the current density is equal to electrical conductivity times the electric field. So it's like you have a conductor here, and when you apply the electric field at here, plus and then minus, and then inside the free charge, this for example copper, the metal have always the free charge that can move, and this free electron will flow to the positive the electrode, right? And that makes the current. So that movement is converted to the J, the current density over the area. And if you apply the very strong electric field, the movement of the charge will be faster, and the more charge will move. Where is it? And let's drive we know that the Ohm's law is V, the potential, electric potential V is equal to I and R. The I is the current, and the R is the resistance of the material. And can we derive this equation from this Ohm's law? Let's think about that. So we have a copper cylinder. That area is A, and the length is L. And think about the electrical resistivity. and this has the resistance of the R, and then R is, if the material is longer, the resistance increase or decrease? Increase, right? So that's going to be proportional to the length. And if the area is bigger, then resistance, because the charge can move more efficiently over the area because you have a large area to conduct, so that the charge can flow more freely if you have a large area, so the resistance will decrease, right? So the electrical resistivity is R times A over L. Okay? And this is the same with the 1 over sigma, the electric conductivity, by the definition. Okay? So the sigma is, what is it? L over RA. And J is what? I over A. And E is V over L. Right? Then if you plug these three equations into the first equation here, then you end up with this V equal IR. So Ohm's law, J equals sigma times electric field, is the same with the V equal IR. Good? So in summary, if we remember all the equation, the Gaussian law of the electricity is this one, and the Gaussian law of the electromagnetism is this one. So this one is the inner enclosed surface, over the surface integral of the electric field is the same with the inside the charge, right? And here is the Q. Gaussian law of the magnetism, because you have a separable poles inside, then N and S would be together so that you have a zero magnetic flux. And the Faraday's law of the induction, that's according to the definition, the change in magnetic field induces the electric field. And the Ampere Maxwell law correlates the current. This is the current. And this is the electric field. They calculate the the magnetic induction field caused by the current and the change in electric field. And in the differential form, so here all the forms are expressed in the integral forms, right? So that's this equation tells that over the surface, some Gaussian surface or over the volume. But if you want to find out the electric field or some magnetic field at certain point, then you can use the differential form. And this is from here, here, and here. So that's another pairs for the differential forms. So COMSOL is the same. You can develop using these four different constitutive equations. You can develop the finite element code or the finite difference code. Similar to that you do the flow analysis or the mechanical analysis. Like for example, the COMSOL program that has a multi-physics function, so that they can analyze the magnitude of the electric field or the direction of the electric field, right? Or the magnetic field too. Right? So that's all based on these kind of fundamental equations.